In the last video, we introduced a concept called Gibbs free energy. In this video, we'll look at the effect of temperature and pressure on Gibbs free energy. We'll focus on the effect of temperature first. Gibbs free energy is defined as H minus Ts. On the first side, if we increase T, then G decreases. In other words, if we increase the temperature of the system, the Gibbs free energy of the system decreases. Overall, the statement is true, but it's not that simple. This is because H, the enthalpy, and S, the entropy, are also functions of T. At a fundamental level, both H and S are functions of Cp. Cp is the specific heat at a constant pressure, which is a function of T. Here is a graph plotting Cp as a function of T. As you can see, as T increases, Cp also increases. Now, let's look at the effect of temperature on enthalpy and entropy separately. For enthalpy H, dH over dt at a constant pressure is Cp. So if we plot H versus T, this is the curve, and the slope of the curve is Cp. There's one thing I'd like to draw your attention to. If you look at the intersection of the curve to the x-axis, enthalpy is defined as 0 for a material at 25 degrees Celsius or at 298 K. Next, we'll look at the effect of temperature on entropy. ds over dt at a constant pressure is equal to Cp over T. Again, let's draw the graph, and here's the graph of entropy versus temperature. Another point I'd like to draw attention to is at 0T, entropy equals to 0. This is because at absolute 0, there's no randomness. Let's have a look at the effect of temperature on enthalpy and entropy together. In both cases, when T increases, H and S increase. Next, let's draw both H and G in the same graph. Here is the curve for H. We also know that G equals to H minus ST. When T is at the absolute 0, G equals to H. We know that both G and H, they start from the same point. But overall, when the temperature increases, G decreases. When considering H, S, and T together, the gap between H and G, from the formula, you can tell that's just simply ST. After understanding the effect of temperature on Gibbs free energy, now we can understand why materials are liquid at high temperature but solid at a lower temperature. We first draw the effect of temperature on enthalpy for both solid phase and liquid phase. Here is for the solid phase, and this curve should intersect with the x-axis at 298 K. For the enthalpy curve of the liquid phase, we use the dashed line. The enthalpy of the liquid phase will be higher than the enthalpy of the solid phase at all temperatures. And the gap between these two curves is the latent heat for melting. Next, we'll draw the Gibbs free energy of the solid phase, and dashed line to draw the Gibbs free energy of the liquid phase. Again, in both cases, at 0 K, G equals to H for both solid and liquid phases. Since nature tends to follow the lowest energy, so here we just highlight the lowest energy phases. At a lower temperature, the solid phase has a lower Gibbs free energy. At a high temperature, the liquid phase has a lower Gibbs free energy. That's why we have materials being solid at lower temperatures and being liquid at high temperatures, when the temperature exceeds the melting point. Before wrapping up today's video, we'll also look at the effect of pressure on Gibbs free energy. We'll do that rather briefly. Let's use iron as an example. At low pressure and low temperature, we have the BCC phase, like the ferrite phase. At low pressure, high temperature, we have the FCC phase, that's austenite. Then at high pressure and low temperature, iron can exist in the HCP crystal structure. This is because at higher pressure, the Gibbs free energy of the HCP phase is lower than that of the BCC phase. So far, we have been looking at the Gibbs free energy of the single component systems. In the next video, we'll look at the Gibbs free energy of binary systems.